So if you haven't watched the previous question, please start with that one because that is an introduction to ice tables with actual numbers, and now we're going to have some variables in here. So it says, consider the reaction below. The reaction begins with only a concentration of HF of 0.1 molar, and the equilibrium constant Kc is 6.6 times 10 to the minus 4. What is the equilibrium concentration of H3O plus and F minus? So we're again going to need an ice table, which is initial, change, and equilibrium concentrations of each of these things. And they are going to be in units of molarity, which I'm just going to indicate up there like that. Note that since water is a liquid, we don't need to consider its concentration. It's not in the Kc expression. If you'd prefer, you could start by writing the Kc expression. So the reaction begins with only HF. So the initial concentration of HF is 0.100 molar, because that's what it tells us in the question. The initial concentration of H3O plus is 0, and the initial concentration of F minus is 0, because the reaction only begins with reactants. There isn't any of these at the beginning of the reaction. We're now going to have a change in concentration here. In this case, what we're going to do is we're going to gain some amount of each of these. Because they're one-to-one stoichiometry, if we gain x of this one, we're going to gain x of this one. So in this case, we're going to have x at equilibrium, and we're going to have x of this. The reason these two things are equal is because for every one of these that reacts, we get one of these and one of these and one of these as well. So one of these reacts with one of these to form one of these and one of these. So if we get x of this, we must get x of this. We don't know what the concentrations are, so we're going to use x as kind of a placeholder. Well, in this case, we're going to lose x amount of this, because x amount of this is going to form x of this and x of this. And as I said in the previous question, because we're in constant volume, you could subtract and add molarities, usually subtract, and in this case, well, I don't know why I said usually subtract. So you can subtract and add molarities. So at equilibrium, we're going to have 0.100 minus x. Now, in order to avoid using the quadratic equation, we can ignore this x if it's less than about 5% of the initial concentration. Now, this will vary based on different books that you read. Some will say 10%, some will say 1%. It depends. But if this concentration, this x, is less than 5% of the original 0.1 molar, we can go ahead and ignore this x. Basically, for the homework set and for the randomized online homework, you can always ignore the x. And if I write the test, you can ignore the x on there too, because you don't have to use the quadratic equation. All right, so let's take a look at this. So if we go with Kc is equal to products over reactants, we've done this a bunch of times now. So H3O plus, F minus are your two products. Note that your only reactant here is HF, because we don't include H2O. Now we know Kc, so it's 6.6 times 10 to the minus 4 equals x times x, which is x squared, divided by 0.100. Note that I'm ignoring this minus x, so I don't have an x squared and an x term. If you do that, then you have to use the quadratic equation. Note that I'm allowed to do this if this is less than about 5% of this. Different textbooks will say different things. Cross multiply, and we get x squared equals 6.6 times 10 to the minus 5. Take the square root of both sides, square root, you can ignore the negative answer. So x is just equal to 0.0081 molar. Okay, so this is how you can find the equilibrium concentrations of H3O plus and F minus. Again, we ignored this because it's less than 5%. In this case, it's about 0.8%. Okay, oh no, it's about 8%. Sorry, because this is 0.1. So it's about 8%. All right, but we can still ignore it in this example.